So now the three-phase generator types in configuration. So we can connect it either Y connected or delta connected. So first on the Y connected, previously I already mentioned, let's say you have three phase just like this, and if you connect on portion of these three phases, then it will give you a Y connection. So on portion of these three phases are connected, are combined to this point N, and now this is just like more of Y. So that's why we are calling it a Y connected generator. So it has three phases. This is EAN, the voltage that is generated, and this is ECN, this is EBN, and similarly these are the phase currents, phi G, and similarly this one. So these are phase current. So now we will focus on two things. One is line, another is phase. So there are two types of components, both for voltage and current. One we call the phase component, another we call it line component. So phase component, as the name suggests, that means it is the value of phase. So this voltage, this is the phase voltage, and similarly the current in this phase, it is called the phase current. And if we want to call the line components, then line will be line to line. That means this is a line. So we have a three phases, and we have connected these phases to a three-phase load. So obviously these are three lines by which we have connected our load. Then this from line A to line B, if this is a voltage, then we call it line to line voltage, or simply just line voltage. But whenever we will measure just voltage of a single phase, then we will call just phase voltage. So phase voltage, this could be either EAN or ECN or EBN. These are the phase voltage. And the line voltage, this could be EAB, that means from line A to line B. From line A to line B, this could be EAB. So these are the line components, line voltage, and similarly we have phase components EAN, BN, CN. And similarly for current, we have also line current and phase current. So the current across this phase is called the phase current, just like this one, and the current across this line is called line current. But for this Y connection that we are observing now, the line current and phase current both are equal. Since this Y connection, this current is just being delivered through this line to load. That's why for Y configuration we have the line current equal to we have our phase current. So remember this, for Y connection, the line component of current and phase component of current both are equal, but the voltages are different. So you can understand, first of all, let's say this is the line phase voltage. Similarly, this is the phase voltage, but what will be the value of EAB, that means line to line. So this should be from here to here. So this incorporates both EAN and BAN together. So I can write EAB equal to, these are vector quantities, so EAB equal to EAN, then this is BN. I can write it, since this EAB is the vector sum of these two. You can understand. So in case of Y connection, I am saying it again, the line current and phase current are equal, but the line voltage and phase voltage are not equal, and they have a relation. We will derive it. So first portion here, these are equal, I already mentioned, and this is the notation. So whenever we write AB, that means this is line voltage from A to B. This is BC, that means line voltage from B to C, and these are the phase components, that means EAN. So N is our neutral point, that means the combined point of these three phases. So EAN, that means the phase voltage of phase A, and similarly others. So now we want to determine the relationship. So I already showed you here EAB, that is the phase voltage, that is the line voltage. We can write it EAN plus BN. So that is written here. Oh sorry, I think I'm missing one thing. Okay, let me clear it all first. So here EAB, that means from A to from B. So we have first EAN, and if you observe the notation, so it has minus here and plus here. So obviously it should be, since this is the EBN, so if I write it plus here minus here, so this will be ENB, right? So EAN then ENB. So EAB, this should be EAN polar vector. So EAN, that means this portion, and then this should be this portion. So this should be ENB. ENB. So this is the correct explanation. So now here EAB, this is EAN plus ENB, and you know that ENB is just the opposite of EBN. So you can write it minus EBN. I just shown it. So these are vector addition, right? So obviously we need to perform the vector addition, and we generally perform this in terms of drawing. So first of all, we know that three phases, they are displaced 120 degree to each other, and we want to add EAN with ENB. So first we have EBN already, so we know that to have ENB we need to reverse it. That means this direction appears our ENB. So if I draw it again here, so these are all phase components. So initially this was EBN, and then if I reverse it in this direction, then it will be ENB, and you know that total angle was 120 degree, and so this one will be 60 degree since all are equally distributed. So this one is 60 degree, and the magnitude of this ENB and this was EAN, both are equal, right? So when the magnitude are equal, so you know that the resultant will be just the middle of this angle. So that's why the resultant voltage, that is the EAB, since we have given it, the resultant EAB will be EAN plus ENB. That's why the resultant appears at 30 degree angle, because you know that whenever two forces or two vector quantities are equal in magnitude, then the resultant will be, the resultant angle will be the middle portion of total angle. That's why this is the 30 degree angle. So now we want to drive it. So here this is drawn it again. Let me clear it. So to have a clear explanation, so let's say we can draw at an angle here from this EAN to, okay, so from EAN to here we can draw at an angle. So this is drawn here, so at an angle, that means we can draw a perpendicular axis, that is 90 degree. So now it is the middle portion of this EAB, okay, since they are equal in magnitude. So since this is the middle portion here, so if I write it as x and another x will be here, so I can call it that EAB, this should be 2x first of all, and then this is 90 degree, and also it is already given that this is 30 degree. So here a right angle triangle has been formed, and in this right angle triangle, this AEN, this is the hypotenuse, and these are two other legs. So you can write it, let me clear it all first. So now if you take the cos of this angle, that means cos 30 degree, cos of this angle, so you know that cos equal to base over hypotenuse, right? Base over hypotenuse. So what is the base for cos 30 degree? Since this is the angle, so base is obviously x, so that's why base is x, and our hypotenuse was EAN. Then we can write x equal to hypotenuse, that is EAN, multiplied by cos 30, that is written here, x equal to EAN cos 30 degree, and then cos 30 degree is basically √3/2. And previously I showed you that EAB, that is our line component, this is 2 multiplied by that x. So now 2 multiplied by √3/2 EN, that results √3 of EAN. So we have derived the equation, that means our line voltage is √3 times of our phase voltage. So for EAB we have derived it, so we can write it EAB equal to root 3 times our previous EAN. Now let's focus on the angle. So let me clear it all first. So now the angle, so you already noticed that this is our reference of phase component, but we have got the line component at an angle of 30 degree, plus 30 degree. So that's why here we have written it plus 30 degree, and previously our phase component was just EAN angle 0 degree. This was our phase component. But whenever we want to write it for line component, so it is multiplied by root 3, and also the phase angle, this is plus 0 degree plus 30 degree. Why? Since if you notice here in this figure, our line component appears plus 30 degree above our phase components. So this is for A phase, and similarly we can show it for other two phases as well. So our second phase which was minus 120 degree, so first of all it should be multiplied by root 3, and also we should add plus 30 degree in angle. That's why it appears root 3 bn minus 90 degree, and also we can write it plus 270 degree. Why? Because minus 90 degree equal to plus 270 degree. If you subtract 360 degree minus 90 degree, then it will result you 270 degree. So obviously minus 90 degree angle is equal to 270 degree angle, so you can write it. Similarly our third one, that is ECA, so it can be multiplied by root 3 and our previous angle minus 240 degree, and now we can add plus 30 degree. Why? Because these are the phase components. So we got the line components of voltages. So we have derived the relationship between line voltage and phase voltage. So how do we got? The magnitude is root 3 times of our phase component voltage, and the phase is plus 30 degree. So now we can write it in words. It is just written. So I just said that the magnitude should be root 3 times, and also the phase is difference is 30 degree. And again the phasor sum of this line voltage is 0, just like our previous things. So since these are also 0 degree, the phasor sum of these 3, and these are the phasor sum of these 3 should also be 0 degree, since they are also now displaced at an equal angle. So they are shifted by 30 degree in each axis.